Everybody, and welcome to the final session for today for PyCon 2017. Before we start, I would like to ask that if you have electronic devices that are liable to make noise, that you try and convince them not to do that, because when they do it, everyone looks at you. Our next speaker is Jessica Lundin, and she is talking about putting Python machine learning in production. Please make her feel welcome.
Hi there. So I am a data scientist and I manage a machine learning team in Microsoft Research, and I'm actually in the field of healthcare. And we are hiring. We're hiring both machine learning scientists and developers. So I will have a link at the end, and I encourage everyone to check out our careers. So today I'm talking about Python machine learning in production. And I hope that you agree, just starting off, that machine learning is a very rich topic. It is quite big. And we have 30 minutes between you and Portland happy hour beer, so we should probably not cover everything. But instead, I'm going to focus really on this concept of how you productionalize models and some of the challenges that arise there, because there really are so many. In terms of the level of this talk, let's just make it clear, this is a common level talk. So really designed that people who may not be familiar with machine learning can get something out of this and actually become a little more acquainted with some of the challenges. I genuinely believe that as tech workers, the more people across the team are familiar with both the strengths as well as the challenges of machine learning, that will all make better individual workers and ultimately better products. So I hope you agree. And certainly, I'm more than happy to speak about some of the more complex sides of machine learning. It is something I just genuinely love, and there is so much cool stuff happening, both in the industry as well as in Microsoft and at Microsoft Research. I have put code for this talk online. You can check out my Azure notebook. It's under Lundin machine, and there's a link for that. You can also see my Twitter handle. So finally, that takes us to the title of Snakes on a Hyperplane, and if you're not clued in on the joke, then I will explain that a little bit later. But first, I'd like us to get a little warmed up on what is this machine learning concept. And of course, in this room, we're tech enthusiasts and we're already on board, but we'll just remind ourselves that machine learning is this field of learning patterns and data through algorithms and ultimately making predictions from these learnings. And there's a lot of examples in tech, right? So many. And I would really love to hear more about some of the problems that people in this room are working on, because I'm sure there's so many experts in not only machine learning, but also statistics. So if you can look away from this cat gif, then you are like so much further ahead of me, because I can't. But there's some really famous examples of machine learning in the industry, right? So there's the cat results, where Andrew Ng was actually able to recognize cats in videos, and he was previously at Stanford at that time and has since moved on to Baidu and moved on since then. Looking at handwritten digits, this is a problem that Jan LeCun is probably most famous for. He's at Facebook, and this is sort of the intro-level problem when you dig into neural networks. So it's been referred to as sort of like the fruit fly equivalent of machine learning, sort of the test case to get warmed up and how to use convolutional neural networks in particular. Something a little bit closer for my interest is actually looking at healthcare. So we can do things like recognizing cancer, malignant cancers from medical images. And this is an image from the Kaggle Data Science Bowl. Maybe some of you actually participated in this. And you can take these CT scans and actually do 3D imaging and hopefully recognize cancers from that. So now that we're more on board with, okay, this is machine learning, predictions, let's talk a little bit more about getting into production. Because again, this is a non-trivial step. It really is tricky. So the way this generally works is we start with our pre-production data, right? So we have some sense of a data set that we're training a model from. So we do that in the blue box, and then ultimately we get some baseline metrics for how well our model performs. So great. We can all do this, potentially even in memory on our own computer. But then what happens when you go to production? So you publish your model, and on your production data, this is a separate pot of data, and apply that same blue box model. What you get is your metrics in production. And if you're really lucky, and in the unusual case, you might get the exact same numbers, right? The same results, the same production metrics. But more than likely, it will not be the same. And why not, right? Well, first off, if your performance metrics actually outperform your training, your offline pre-production, then you already have a red flag, because that's pretty much basically impossible. So you already know, okay, well, why is that? Well, maybe your production data is situated in your feature space where your model is particularly performant. But you need to have an answer why, so you'd have to dig in and figure that out. But more than likely, your results will be, your accuracy, et cetera, will be less, and then it will be a question of why, and how can you boost that accuracy and explain those results. And ultimately, it may involve retraining your model as part of your production environment. So we're going to get into two highly visual examples, because again, I'm going to assume that you walk in here and know nothing about machine learning, but maybe you do, and you can appreciate that there's some cool visuals. And there's also some recommendations for ways to handle some of these tricky problems. The first problem is this issue that your production data is probably not going to be exactly the same as pre-production. And let me give you an example from my own work. I build models on our beta users, right? So I work at Microsoft, and the beta users come from my fellow peers. And as you can imagine, we're not going to be a standard representation of our larger population. So anything that I train on my beta pool won't necessarily extend beyond that. And this is going to be something that is common until you actually have some production data to test on itself. So here we have synthetic data, and this is for a binary classifier. So binary, 2 classes. We've got the same number of data of blue checks and red squares. So it's a balanced data set. And what we're going to do is fit a model to separate these classes. And what you see here is a logistic regression, so a linear separator. We're literally drawing a straight line to separate these different data classes. And there's a little bit of code here. Again, you can go to the Azure Notebook for Lundin machine, and you can see all of this code. So we have 95% accuracy for this particular case. So we're doing pretty well in our pre-production space. But what happens when we go to production? So this is to simulate, on the left, our pre-production data, and then on the right, our production data. And the production data has some faint gray circles, so you can differentiate by eye. So on top of the blue checks and the red squares. So I hope that you can see that it's essentially flipped about the 0 axis on the y-axis. So the blue squares are sort of, or blue checks are sort of switched, and the red squares. So our linear classifier is sort of set up to fail, right? How could you possibly draw a straight line through here? And with the current setup, it is not possible. The production accuracy, in case you can't read that, in this case is 5%. So we went to production, and what happened is our feature space is just very different. And this is absolutely the case that this could happen. So what to do next? Well, luckily, there's several different ways that we can handle this. One way is you pull out a bigger hammer. So instead of treating this as a linear problem, we can switch and use models that do better with nonlinearities. So on the left, I'm showing a random forest. So this is an ensembling method, building trees. And you can see here now I have accuracy of 100%. And I hope that you already see that I might be subject to a little bit of overfitting down the road. You can see there's some little blue islands where we're just fitting that one little blue check. So it may not be so robust, but certainly the accuracy is high in the near term. And then on the right, there is a support vector machine approach. And here, using our radial basis function as the kernel. And here you can see that we're instead of just drawing straight lines to fit all of our data, we're actually able to include curvatures and better represent the differences between these classes. And here an accuracy of 93%. So these are both totally valid ways to go. And certainly there are a lot more algorithms. These are some of the more popular ones out there. So okay, we handled this problem, pulled out a bigger hammer. But what are some other ways that we might handle this? One is that we could do some feature engineering. And feature engineering might be not always held up as the most, maybe not as interesting as some other ways that people publish papers in this space, but it is so powerful. And I think personally that it is one of the best ways to really get high accuracy in the long term is to be really clever with your features. So one way that we can approach this problem is go back to our linear classifier, or logistic regression, and instead build out some new features. So I hope that you can see on the left side of the screen, there's our standard x1 and x2 that we've seen through the slides. But now on the right side of the screen, you can see I have an x1, and I made a new feature called x1 times x2. So here you're able to see that the blue checks that have a negative sign in either x1 or x2, those actually are below that x-axis for the most part. And our linear classifier is able to actually separate these. So good news, we're up to 90% accuracy now, so that's much better. And there's a few more points to make here, right? That especially when we think about going to production, it really behooves us to think about the simplest model that gets great accuracy. Certainly we would want higher accuracy, among the top in this case, but consider that linear methods are both more performant in terms of runtime, certainly than ensembling methods. The guarantees of convergence are going to be generally higher. And also, linear models are interpretable, and we definitely care about that. It's just always going to be so much easier to understand what's going on underneath the hood with a linear model. Okay, so if you're not on board with machine learning, just skip this slide and don't sweat it. But if you want to take this a step further, I definitely want to provide those sorts of resources. What we're looking at here is the potential where you have differences in your distributions, right? So what are some ways that you can approach this problem in general? Because it really will come up pretty much every time you productionalize models. So one way is visualization. And we really did step through a couple of ways to do this. But you can look at histograms, pair plots, other ways. If you want to take a step further, this is really fun, is you can actually do clustering, so unsupervised methods on top of supervised methods. So basically, you can visualize your clusters and look if your production data, it forms its own clusters that are not represented by pre-production, then that's pretty much a warning of like, oh, hey, we should probably have a look here. Finally, looking at KL divergence. This is something you can do in your feature space, and it's a way to quickly evaluate if again, you have these differences in distributions. We're going to switch gears and talk about a different problem that, again, is very common in production problems and an elegant way to solve it, a very visual way as well. So we're looking at unbalanced problems, and these are very common. Think about fraud, right? Fraud is relatively rare. And that makes it a much more challenging issue. It turns out that quite a lot of problems are going to be unbalanced, where you have a majority class, in this case, the red squares that are 98% of the data, and then we've got 2% of these fraud cases. And looking at the histogram, it's just another way to represent this data, right? So you can look at the 0 class and see that it's going to be most of my data, but a few rare cases of the fraud. Okay, so how to approach this? If I pull out my logistic regression again, it might be the case that you predict everything is of the same class, because why? Well, when you only have a few cases, it's actually hard to characterize your rare event. So rats, what are we going to do here? we're going to pull out some metrics to help us on this journey, right? And we talked previously about accuracy, but now we're going to pull out a few more. So here we're going to look at precision and recall. And precision is defined here. It's currently 0, recall 0. But what are those? So precision is going to be the sum of your true positives over your predicted positives. So predicted positives in this case was 0, because I guessed everything was going to be of the majority class. So that's going to be 0. And then the recall is actually also 0, but that's your true positives, which is 0, over your conditioned positives, like the ones that are actually truly positive. And in this case, that's 2, but 0 over 2 is still 0. OK, so we have some metrics to help us evaluate in the future. But we're still back to this unbalanced problem. So one way that we can go about this is what's called oversampling. And the way to explain this is you can essentially upsample your rare class. So what this means is you pick out by random from your rare class, add a little bit of noise, and then put that data back in your data set. And then replace that sample back in, which is what's called replacement. So it doesn't go away. You can keep using it randomly. So now I have 50-50 data. It's totally balanced. So this is going to be great. And I can pull out my same logistic regression. And this time, I get a sensible answer, because I can really characterize those rare events. And again, we can pull out our metrics and say, all right, now I have 100% accuracy, which is usually a red flag, because anything that's 100% is like, it usually is okay, maybe not right. In this case, we can see visually that it is. But we also see now that our precision and recall are at 1, so much better. This is just one way to handle this problem, and I'm certain that in this room there are many other ways that people approach this, and I would certainly be interested in hearing about it. But when you suspect that you have, or let's not even suspect, you can measure if you have an unbalanced problem, there's several ways you can go about this, and these are ordered in terms of complexity. So one way is that you can do this cost-sensitive classification with what I described as the rare class upsampling with replacement. You could call that oversampling. Some people do undersampling. That could also be on the list. There's importance weighting. This is a standard technique if you want to take that further. And finally, you can look at boosting. And certainly, there's a lot of really nice examples of boosting in the machine learning competitions. So XGBoost, you can do ADA boosting. There's a lot of ways. Essentially, boosting in a nutshell is that you penalize your model where you incorrectly estimate. So if you miss the guess of the fraud cases, you penalize your model and then reevaluate. So one of the coolest things about machine learning, there's actually a lot. So my list is very long. I love this topic. But what I think is just so cool is how creative it is, right? So in this case, I laid out, this is a supervised way to approach the problem. All the data are labeled. But what if you want to think about it instead of an unsupervised problem? So you absolutely can. You can treat this like an anomaly detection problem. So what you do in that case is you look at your majority class. And you need a lot of majority class to characterize what the normal event is. And from that, you can use what's called a one-class SVM, and you can then try to predict what are your outliers. So lots of different ways to do this. OK, so now we're going to come back and talk about hyperplanes, because it does warrant a little bit of description. So you can see in this image that on the left side, there's no way to draw a straight line through this data. So you could say that your data are not linearly separable, right? So what you can do is transform your data into a higher or infinite dimensional space where you then can separate your data linearly with a line or with a plane with a hyperplane. And in particular, this is associated with SVMs, and this is what's called the kernel trick. I'm going to supply one last little piece of advice, something that I've learned about productionalizing models with a few different teams, and that is just some back-end maintenance. Logging is just so critical for having accurate models in the long term. It's the case that we don't just sort of lob our model out there and then say, okay, well, my work's done here, but instead what it signs you up for is a monitoring requirement to make sure that everything is checking out. And it's just so important, right, as builders of software that we care about our customers at the final end and that they're getting very accurate models the best possible. So logging timestamps and instance IDs, the sorts of things that will set you up to be able to completely recreate the things that you don't expect that might happen later down the road. Thinking about runtime, taking a little bit of an I/O hit to capture that runtime. For a lot of problems, your spec may include that you have sub-second runtimes, particularly when you look at fraud, serving ads, things like this. It needs to happen very rapidly. So is that model actually performing within the specified time is very important. Also, we want to think about performance metrics. We talked about 3 different metrics. There are so many more. You can basically create a scorecard and actually track through time what the drift in your performance might be. And that's quite helpful. Typically, model convergence won't be a problem because you're going to be so smart about setting up a robust model beforehand that you won't ever have this problem. But I can tell you that sklearn actually only throws a warning if you have convergence errors. So you definitely want to keep track of those. Again, this is the case where using linear models is favorable. So you have less likelihood of this. And one of my biggest pieces of advice, this is totally uninteresting. You take data science, it's like the sexiest job in the 21st century and all these things that make it sound extremely cool, and it is. But auditing is so tricky and hard and frustrating sometimes because it really is this task of like, okay, this thing broke. And it's taking all of that logging data, all of that telemetry, and piecing it together into a coherent story of what went wrong. And it really, I think it's sort of a bit of a paradigm shift, actually, in terms of building software, because it requires us to really care so much about all of that nitty-gritty detail that results in a final product that is really good in the long term. So in my group, we actually trade among the scientists. We say, hey, do you mind spot checking my model in 20 places? And we trade this task off because it's a little onerous, but again, just so important. I'm going to go through a few resources because after this talk, I know you're so excited, like I am, to go do more machine learning. There's the Introduction to Machine Learning from Stanford, and this was put on by Coursera. And it's really a classic, very, very well thought out. That's programming in MATLAB/Octave, in case that's important to you. Then there's the canonical book, which is Elements of Statistical Learning. This is a free PDF, so go ahead and have a look. And I think you'll not be disappointed in terms of the coverage of topics. If you really want to get started right away and get started with data and really well done tutorials, I don't know if there's a better resource than Kaggle for this. They have both Python and R tutorials. So you can get started on the Titanic data sets, predicting who will survive the crash and this sort of thing. In terms of machine learning in Python, just some packages that you'll find helpful is I use scikit-learn. This is all in the Azure Notebook. There's a ton of neural network packages that are coming out. These are all on GitHub that I've listed here. And finally, you can actually put a wrapper around R because R is really quite good with the CRAN package. So I don't shy away from that because as much as I love Python, I always want the best tool for the job. And a lot of times R is quite good. Microsoft is growing Python resources. I totally encourage you to check out our booth here. There's the Azure Notebook that I was using, which is really quite seamless to host your notebooks. But there's several other bits. So the Azure SDK, we put on an intro to Python MOOC. Then there's also Python plugins for Visual Studio if you want something a little bit more developer-friendly. And finally, our neural network package, I mentioned it before, but CNTK, which is actually highly performant. It's very well distributed and actually scores quite well in terms of runtime performance. And finally, I'm listing the job URL as well as the job numbers for our team. Again, both looking for machine learning scientists as well as people passionate about being in the healthcare space for developers. So thank you for your time.
Thank you, Jessica. And if you have further questions for Jessica, she'll be out in the hallway. You can chase her up later. Lightning talks will be starting in Hall C in about 5 minutes. Thank you very much. Speaker finish.